Hello everyone, I am Yash from University of Maryland and I am going to present the paper Integrating Planning and Acting with the Re-Entrant HTN Planner. A major problem with integrating HTN planning and acting is that unless the HTN methods are very carefully written, unexpected problems can occur when attempting to replan if execution errors or other unexpected conditions occur during acting. To overcome this problem, we present a re-entrant HTN planning algorithm IPyHOP that can be restarted for replanning purposes at the point where an execution error occurred, and an HTN acting algorithm run lazy refine ahead that can restart the HTN planner at the point of execution failure. We show through experiments that our algorithm is an improvement over a widely used approach to planning and control. So, how does it work? IPyHOP produces a refinement tree as its planning solution. Here, the refinement tree is the tree of task decompositions leading to the solution plan. Now, if execution errors occur, run lazy refine ahead sends IPyHOP a pointer to the exact place where the replanning is needed. The image at the bottom shows a sample refinement tree. Let's assume that the primitive action put down GFL fails during execution. At this stage, run lazy refine ahead sends IPyHOP a pointer to this task in the refinement tree and requests replanning. Before I show the results of our approach, I would first like to quickly introduce the planning domain we used for our experiments. This domain is called the RoboSub domain, and it was inspired from an actual robotics competition, the RoboSub 2019 challenge. In this challenge, teams had to develop an autonomous underwater vehicle, AUV, that performs various tasks. The challenge modeled an imaginary underwater realm where our robot had to perform multiple tasks like picking up garlic, crucifixes, slaying vampire, decapitating and staking Draculas, etc. In our experiments, we compared our run lazy refine ahead algorithm to the run lazy look ahead algorithm for integrated planning and execution. The key difference between these algorithms is that when execution errors occur, run lazy refine ahead sends IPyHOP a pointer to the task decomposition tree, whereas run lazy look ahead tells IPyHOP to plan for the initial task starting at the current state. Here we show the results of the total iterations taken metric. This metric calculates the total number of iterations taken by the planner for a given planning problem. Calculating iterations provides a good estimate of the planner's total planning time. The total number of iterations taken by the planner for run lazy look ahead is presented as blue histogram and run lazy refine ahead as purple histogram. The relation of this metric for the two deliberative acting algorithms is visualized as a scatter plot in the right. This slide shows the results for total cost of actions that were executed. This measures the total cost of an action sequence for a given planning problem. Execution of smaller action sequences will generally lead to lower total action costs. Based on our results, we can state that run lazy refine ahead is approximately 20% computationally faster than run lazy look ahead for integrated planning and execution. Also, we found that run lazy refine ahead produces approximately 30% cheaper execution sequences than run lazy look ahead. This concludes this brief overview of the paper. I hope you found this interesting. If you want to find more about our approach or discuss anything regarding this paper, please come to our poster. Hope to see you soon. Thank you.